All right, good morning, everybody. It is now rapidly accelerating towards the end of the semester. Just as a reminder, Thursday is a wellness day, so there will be no class on Thursday. This will be our continuation of MDP, and then we'll be talking about reinforcement learning. I have been using as a running example this kind of concept of a robot in your room that's helping to clean and tidy your room. Remember, we thought about that as a Markov decision process because we can think about the room as the state, kind of the description of the room as the state, and then we think about the robot as taking an action. What could possibly go wrong?
Yeah, what could possibly go wrong? So imagine that the robot's getting some points for picking up trash or cleaning up or tidying up, and the robot is designed with this long-term reward. So the more stuff it picks up, the more points that it gets, right? That seems very reasonable. So I have a real life example of this, not with a robot, but with my kids who were at the time 4 years old. And they got M&Ms for doing cleanup after dinner. And at one point, you got one M&M for finishing your cleanup. This is a relatively small, right? And they wanted more. So what they did is they threw all the markers onto the floor, and then they cleaned them back up again. You've done 2 cleanups. We want more M&Ms. And of course, a robot is going to be even more clever about this. And if you design one of these, if you set up this world, it will actually, dump out the trash so it can keep picking up trash.
So it will pick up the trash. It will get a reward. And then it will okay, what if I dump the trash again? Then I can pick it up again and I can get.
Because then I get 2 rewards, twice the reward that it initially got. Dump it out again, you get it 3 times. So just to point out that reward design is really tricky, and these algorithms will hyper optimize. Just think about, I want to get rid of all of my spam email, right? It might just get rid of all your email, right? It certainly got rid of all your spam. So all sorts of ways that things can go in unexpected directions.
Yeah. And the reason this is a new topic in a way relative to things we talked about so far in the course is that whereas labels tend to be clear, it's clear what the labels want to be. Where do rewards come from? And often as let me make up a term, a reinforcement learning engineer, of which there probably are and will be increasing numbers of. One of your engineering tasks would be to engineer a reward function, or somehow get that reward function by maybe trying to fit what experts seem to be doing when they act.
Yeah, and there's so many penalties or considerations there. Like imagine a car and you want it to stay in lane, except when there's like a kid who runs out into the middle of the road, and then you don't want it to stay in lane. You think of it as multiple regularizers, multiple reward functions, but it's definitely really tricky to specify.
And Alexander, I see your note, and that's right. I mean, there are all kinds of things you can think through about how to do this, and you might try to do it also in a way where you don't need to augment the state, so you can keep track of what's happened. You might try to think about a Markovian way. So here you could imagine that there's a penalty for dumping the trash. So if I have a reward for picking up trash and a smaller penalty and a larger penalty, let's say a big, large negative penalty for dumping, then perhaps the robot.
Or maybe every time the room is clean, you get a point, rather than every time you pick up the trash. So there's all sorts of.
Right. I need everybody to do something. I want all of the students out there to unmute. You will understand why in a second. I want everybody to unmute, and I want you all to get ready to make some noise. And the reason why I want you to get ready to make some noise is Finale Doshibella's got tenure!
Congratulations!
Congratulations!
Congrats!
Thanks, everyone.
As featured in the Crimson. We're delighted for you, Finale, and it's just been such a joy to teach with you this semester as well. And I wanted to do that because I remember in 2008 when I got tenure, it was while I was teaching AM-121, and I still remember kind of the students learning about it at the time. So I just think it's nice to share with everybody. So great, we're thrilled that news came down yesterday, and we're going to get into class. So we're going to pick up where we left off. And this is where we were. We were talking about MDPs. And today we're going to continue talking about MDPs, but we're also going to start talking about reinforcement learning. So let me remind you, first of all, about a Markov decision process. We've got our states, our actions, our reward function, and our transition function. So states, actions, reward, transition. And we also have a policy. And I'm just going to write the policy as a deterministic policy. So the policy just will return an action. I know we said that we can generally allow the policy to return a distribution of actions, but we're not going to need that. And we're talking about two types of problems. One type of problem is a planning problem. Planning problems, you are given the model. So you're given this S, A, R, and P. Call that whole thing the model. And your problem is to output a policy. Hopefully a policy that behaves well in the world that's described through the Markov decision process. And there are two types of things you can do there. You can do finite horizon, which we did last class, and you can do infinite horizon, which we'll do today. So imagine that you're going to be acting in this world forever, but we're going to use this discount factor so that you care more about the present than the future. The other type of problem that we will start to talk about is reinforcement learning. And reinforcement learning is this problem, as we'll discuss, that you're given access to the environment, you get to move around, but you have to learn how to act by actually acting in the world. I don't give you a model of the world. We'll get to that in the final 1/3 of class today. So I want to first of all talk about planning infinite horizon. Let's talk about this first. And I want to introduce, first of all, this idea of an MDP value function. This is going to be the expected value of following policy pi from state S, which we can write as the expectation over states that are sampled according to the transition model between states of the sum of the infinite sum of the discounted values of the reward we get for following that policy into the future. So I just want to make sure that you will recognize that this is playing the role. This is my discount factor. And notice that when t is 0, which is the current time period, I've got gamma to the 0, so there's no discounting. One step into the future, I've got gamma multiplied by rewards. 2 steps into the future, I've got gamma squared. So think about your gamma, your discount factor, as being something on the interval 0, 1, we won't think about 1. It has to be smaller than 1. Okay. So that's this notion of a MDP value function. And I've described the discount factor. Now, we'll say the policy pi is better than or equal to policy pi prime if v pi s is at least as good as v pi prime s in all states. So pi is better than pi prime if it's at least as good in all states. And then we'll say that the optimal policy is pi star that's better than or equal to all policies. And it turns out that there will be at least one policy with this property. It's not immediately clear that there would be one policy that's better for all states, but there is. And we'll call one of those policies pi star. There may be multiple policies. We'll just want to talk about any one of those policies that are better than or equal to every other policy pi. Call that policy pi star. That's our optimal policy. And then we have this notion now of the optimal value function. So that's the value function that corresponds to the optimal policy. It's defined for every state S, and it's a policy that maximizes the MDP value function in that state. Now, how are we going to try to solve for the optimal policy in an infinite horizon planning problem? Well, we're going to try to compute this optimal value function. This is going to be the target of our computation. Notice that if you can compute this optimal value function, you'll be able to also extract from that the optimal policy. Because the optimal value function will tell you the value of being in one state versus another. And we'll see that that's going to be enough for you to decide how to act in the world as well. So this will be the target of our computation, how to compute this value function. And for that, we'll use this idea of the Bellman equations. You can also think about this as the principle of optimality. And this says that the optimal value function will have the following structure. Think about this as a consistency property involving the value function across states. Oops. Let me explain this. This says that the value of a state is equal to the value of the optimal action in that state plus the value of continuing optimally. It's a consistency property. It says if this is the value of following the optimal policy in the current state, then it had better be that it's equal to taking the best action now, where I think about the immediate reward for taking an action now, and I think about the states that I'll land in S prime, and the value I'll get for following the optimal policy from those states. So it's a consistency property. And this leads to the following algorithm, which we'll call algorithm 1, and is value iteration. In this case now for the infinite horizon planning problem. And the idea here is that we will, let's call this equation box. We will solve for box iteratively. Notice that this equation looks a bit nasty. Like if the goal is to try to find a value function that satisfies the self-consistency equation, it looks nasty because there's a maximization in it. So it has this nonlinearity. So what we're going to try to do there is we're going to hope that the following recipe will work. We will initialize the value to be 0 for all states. And then we will repeat, and this is the iteration step. And we'll do that for all states S. So notice that I'm using my current value function, V, and I'm pushing it through. You can think about this as a one-step look ahead. I'm pushing this through my Bellman equation, and I'm getting an updated view, which I'm writing as V prime of the value in that state. And you do that for every state. And then at the end of this step, you now will set Vs to V prime S. So this is the idea. It's kind of a straightforward way to think about. If you think about we're trying to find a fixed point of this equation, notice this has V star on the left and V star on the right. So we keep pushing through that, and we're trying to find a value function that is a fixed point of that update. And theorem is that value iteration will converge to the optimal value function, V star. And I want to give you some intuition for why this works. But first of all, let me just pause and make sure there are no clarification questions before I give you the intuition for why that works. Yeah, Richard.
Yeah. So earlier when we were talking about a policy, is a policy here like a distribution over the possible actions, or is it deterministic? Like, given this state, I will always do this one policy, one action.
Yeah, so I've simplified things for today because we actually will only need policies that are non-randomized. And let me show you how you would extract the optimal policy. So the optimal policy, if I told you V star, you would extract like that. So that will give you your optimal policy. You say, okay, if you know V star, then now you know how to act in the world, and we only need a deterministic policy. You can prove that's sufficient for these problems. Any other questions? Okay, you're right though, Richard. We were talking about randomized policies last class. Let me give you the idea for why value iteration works, and just kind of a sketch of the argument. So the idea will be to show that and we can write this whole thing as a vector. Meaning that, remember, this is you think about V, capital V as a vector if you want, because it's got an entry for every state. And now I'm writing this update as V prime, as V goes to V prime through the Bellman operator. For Bellman, this is called the Bellman operator. And that's just the word we use for this update step. Okay. Call that the Bellman operator. And the idea will be to show that this is a contraction. Let me explain what that means. So this is a bit of an aside, but I think it's just kind of useful for you to have in mind. So let's just consider a function that maps from R to the D to R to the D, and that we use to update X like that. So it takes an X, it applies the function F and returns an X prime. And let's think about what we call the fixed point of that function, which is an X star such that F applied to X star returns the same thing. That's exactly what we're looking for with the Bellman operator. We'll say that function F is a contraction when if you take two values, x not equal to y, and you apply f to x and f to y, the norm of the difference between them is smaller than the norm of the difference between the values you start with. This is a definition of a contraction. So for example, if this seems mysterious, think about f of x as x over 2. Takes x, divides by 2. Imagine x is a real. Then you could imagine x and y might be initially 8 and 2. Then if you apply f, you get 4 and 1. Apply f again, you get 2.5, and so forth. And notice that 1 and 4 are closer together than 8 and 2. And 2.5 are closer together than 4 and 1. So that's the contraction property. And of course, the fixed point of this equation would be x star equal to 0. And then theorem about functions that have this contraction property is that given the contraction property, then f of x has a unique fixed point, and this process converges to the fixed point. And the proof of that is kind of elegant and simple. So suppose that, let's argue, first of all, that f has to have a unique fixed point. Suppose not. If not, then suppose there were two fixed points, x star and y star. Well, by them being fixed points, this would be equal to this, which would violate the contraction property. So there has to be a unique fixed point, because we would need this to be strictly smaller than this for the contraction property. And then moreover, f has a unique fixed point. So to see that, consider some x, I'm sorry, f converges to a fixed point. See that, consider an x not equal to the fixed point x star, and think about what the update does. So in particular, fx minus x star, which is the result, that's the distance between the fixed point and x after we apply the update. is equal to fx minus f of x star by the fixed point property, and then by the contraction property that is smaller than x minus x star. So then the point is that we've been able to reduce the distance between x and the fixed points by applying the operator f. Okay, so theorem, if f has a contraction property, then f of x has a unique fixed point. And by just applying f over and over again, you get to that fixed point. And so then, well, how does this apply to our setting? Well, we'll take just as a fact, I won't show this to you, but the Bellman operator, B, is a contraction for the norm defined as the max over the vector of the absolute value of the entries in the vector. And if you can show that it has that contraction property for that norm, then you can use the theorem I just showed you to argue that it will converge to the fixed point. So I wanted to walk you through that because it's, I think, useful intuition and kind of useful to make things appear not completely mysterious as we go through what we're doing today. And then what I want to do now is I want to show you an example of value iteration at work. So here's an example of value iteration at work. This is in a grid world, much like the grid worlds we've been discussing, where in this grid world, the reward is 0 in all states, except for this state 1, 4 and this state 2, 4. And in those states, you get +1 for taking any action or -1 for taking any action. And then there are no more actions. So these are absorbing states. You bounce off obstacles, much like your homework exercise. The actuator has 20% noise. For example, with probability 0.1, it goes left. With probability 0.1, it goes right when moving up. And suppose the discount factor is 0.9. So here's the optimal policy in this world. You can see that it sends the robot this way if it starts here, because it worries that it will slip into the bad goal if it goes this way. But from here, because of the discount factor, it's actually better to go this way, even though there's a probability you might fall into the bad goal. So what does value iteration do? Well, here's we initialize all the value function to 0 in every state, and then we just keep applying this update step to every state. So the first time we do that, we get this for our new value functions. Notice that the continuation values, V's, were 0s everywhere. But for these two states, I did get a reward of 1 or -1 for taking the immediate action. So that's again, the value function after one iteration. Let's now do the second iteration. So in the second iteration, what we now find is that we get some value now for the maximum action from this state. Now the maximum action from this state chooses to move right. Remember that I said that the actuator succeeds with probability 0.8 and the discounting is probability 0.9. So the reason you get 0.72 is 0.9 times 0.8 times 1. So it reasons that if you're in this state, it looks like you can get value of 0.72 by the continuation value of moving right and then being in this state. So let's put that here. That's after 2 iterations. Now we do the third iteration. You see that the values of the states are kind of rippling out away from this good goal. So we've got these new values now, these new non-zero values. That's after 3 iterations. Let's do the next iteration. Here's what we get. We get more values that have rippled away from the goal. Let's do that again. Now after 5 iterations, notice even the value of this state is improving, because we're learning that if we try to go right but accidentally slip down, we can recover and we can go up again. So there are things like that that are being learned as we do value iteration. Keep going. Something interesting happens between iteration 9 and 10. Notice that we're also annotating the optimal action following the policy extraction step that I described by these little arrows. And notice the action is still wrong in this state here. But when I do my 10th iteration, now the planning algorithm learns that it should move left here rather than right. So there's 10 iterations. Now I have the optimal policy. 11 iterations, 12 iterations, still have the optimal policy. Even after 100 iterations, the value function is still moving a little bit. Notice that this value is now still a little bit different from this value. So relatively quickly, we learned the optimal policy, but we're still improving the value function estimation as we do additional iterations. So just a few comments about value iteration. Value iteration converges to V star only asymptotically. So it may only converge in the limit to the exact value of the optimal value function. But two, this is the good news, the policy can be extracted, the optimal policy can be extracted from V in a finite number of steps. So these are two facts that I want to give you about value iteration. Are there any questions? So again, you're given the model, you iterate. It's trying to calculate this V star thing. Once you have V star, you're done. I think we'll take a couple of minutes and then we'll talk about policy iteration. So feel free to shake out or relax, whatever you want to do for a couple of minutes. We can do exercises like Richard's doing. I think that's always a good thing. And then we can get back to class in 2 minutes. I'm also happy to take questions if anybody has any. So Lillian asks, how is this algorithm different from the finite time horizon? It's similar, Lillian, except we're not keeping track of steps to go because we're just looking for a single policy that we will apply in the same way, whatever the state. Whereas in a finite time horizon planning problem, it's very important that you know how many steps are left. And the value function and the policy function you should use will depend on how many steps are left. That's a good question. Okay, so let's go ahead and get started again. Yeah, Blake.
Oh, just a quick question. Could you repeat how the policy extraction would have worked for the last grid world example? So like when that arrow flipped, was it just that the adjacent square now had a higher value, so we just pick that one instead? Yeah, you just keep using this formula. So for a given state, like that state that we were looking at, you look and you ask, what is the action that is best given my current view? So, okay, this is written for V star, but pretend this formula is written for V, then that would give you the extraction step. Let me explicitly write it down. I think it's worth making explicit. So the extraction step for a given V uses the current value function to decide what's due.
And so the point is, at that point, the value function to the left was slightly better than the value function to the right. And so now it was telling us to go left rather than right. Okay. Great. So now let's talk about algorithm 2. Which is policy iteration. Here's the idea behind policy iteration. We start with a policy, call it pi0. We evaluate that policy to get a value function for that policy, call it v0. Then we use that value function to improve the policy to get a new policy that I'll write as pi1. Then we evaluate that policy to get value function for that policy. I'll write v1. And then we improve our policy again using that value function to get a new policy pi2, and this continues. So there's going to be a flipping between evaluation and improvement. I'm going to explain this to you. So first of all, you initialize pi0. This can be arbitrary. And then you repeat 1, evaluate the value of that policy. So here pi is the current policy. And 2, you improve the policy. Now, how do you improve the policy? You do this. You use your value function. It's kind of like you extract the policy using the value function you currently have. That's the improvement step, and then we will set policy pi to be pi prime. Okay, so take your current policy, call it, let's say pi1, evaluate it to get the MDP value function corresponding to that policy. How well is that policy doing in the world? And then look to see whether there's a way to make that policy better in this improved step. So this is looking for the action that looks best according to the value function of that policy. And if the policy is the optimal policy, this will be the same as the current policy. But the idea is that if the policy is not quite optimal, this might change the action. And I will explain that just a little bit. So first of all, what is the theorem? The theorem is that policy iteration converges to the optimal policy in a finite number of steps. Notice, because it converges to the optimal policy and because we're using evaluation to get the MDP value, this also implies we also get the optimal MDP, the optimal value function. So it has a slightly stronger theoretical claim than value iteration. Value iteration, we were guaranteed to get the optimal policy in a finite number of steps, but we were not guaranteed to get the optimal value function. By the way, getting the optimal policy is much more important than getting the optimal value function, but still. Now, let's just kind of make a note to give some intuition for why this works. Let's suppose that when we do our policy iteration step, there is an action in state S. Suppose for state S, there exists an action A for which we can do better than what is suggested by the current the current policy. So suppose there's an action A in state S, for which if we followed that action, so what does this mean? This means taking the action once, then following pi is better than following pi. That's mathematically what this inequality means. Take the action once, then follow pi is better than just following pi. So that's a note, and that's the intuition for why policy iteration converges. We keep finding actions that by changing the policy to that action leads us to improve the performance. In particular, you can show that the value function is strictly increasing if the policy changes. So that's like a key technical property that can be proved, which I'm not going to prove you that property in detail, but hopefully that gives you the intuition. Now, Richard asks, how do we do the evaluation step? I'm going to show you that in just a second. So hold on just for a moment. I haven't explained that yet. But okay, what's the point? The point now is that one of two things will happen. Either when I do my improvement step, the policy doesn't change. If the policy doesn't change, it means I've found a fixed point, and it means that my policy is optimal, because it means that the policy is satisfying the Bellman equations. Or the policy changes, and if the policy changes, you can prove that the value function has strictly increased. Why does that lead to convergence with a finite number of steps? Because we're in a finite world, and so there are only a finite number of deterministic policies in a finite world. So you can't keep changing policy and have the value increase forever, because at some point you'd have revisited a policy you've already visited before. So we get this nice theory for this. Andy?
Yeah, so I guess then is the advantage here that we have just finite convergence versus like infinite improvement with the value iteration? Like, why do this more complicated process?
Yeah, hold on to that thought. Let's look at a quick example. This is not quite in the same grid world, but it's a very related grid world, and it's illustrative of what would happen in the grid world that I showed you before. So here's a grid world again with a good state and a bad goal state, and here you don't stop in the goal state. So it's an infinite horizon problem where there is also no stopping state. And let's say we initialize the policy to move up everywhere. Then you can show that after one improvement step. What does that mean? You take your up policy everywhere, you evaluate it, and then you do one improvement step, and then you evaluate that new policy. These are the value functions. This is the value function of that new policy. This is after the second improvement step. So now I evaluated that policy, I did an improvement step, I evaluated it again. Here's my new value function. Notice here that your value function can go a little bit below -100 in this state because you don't stop in that state. You may walk away and then end up back in that state again because we have noisy actuators. And then here's after 3 improvement steps. And now it has converged. So it took 3 steps to converge, whereas in the other example of the grid world I gave you, it was taking of order 10 steps for the policy associated with value iteration to converge. And I'm going to get towards Andy's question now. So that is suggestive that policy iteration will tend to converge more quickly. So not just in a finite number of steps, but will tend to converge more quickly. Let me talk a little bit about the trade-offs here. So let's do a couple of notes on policy iteration. First of all, I need to answer Richard's question, which is how do I do policy evaluation? So for policy evaluation, what is the problem? I'm given a policy pi, and I want to find the MDP value function corresponding to that policy. And it turns out that we can solve a system of equations to get the value function. What is that system of equations? It's this system. Notice that because I'm doing policy evaluation, there's no maximization. We had a maximization earlier because we were looking for the optimal action. We were trying to find the optimal policy. When we do policy evaluation, I give you a policy. So now everything is linear. The value of the policy in this state is equal to the reward you get immediately plus discount factor multiplied by the expected value from the policy in the states that you land into. Notice also it looks a little bit tricky because I've got how many, well, in a sense, because I've got the same variable on the left-hand side as the right-hand side. But also the really good news is that I've got S unknowns, where S is the number of states, and S equations. And so linear algebraically, we can solve the system of equations to find the solution, which is the value for every state S. And just to see this, you can write this whole thing in vector form. So let's write that as V pi equal R pi plus gamma times the transition matrix multiplied by V pi. These are all vectors now. P pi is a matrix. So P pi here is a S by S transition matrix. So this is the same expression I wrote above. I'm just writing it in vector matrix form now, but nothing has changed other than that. These are S-dimensional vectors or matrices. And now linear algebraically, this is I minus gamma P pi times V pi equal R pi, and then I can invert and get V pi equal I minus gamma P pi minus 1 R pi. So you do need this matrix to be invertible. It will tend to have full rank. You need this to be full rank. Oops. But it will tend to be full rank because the transition matrix will tend to have different transitions for different states. And so because of that, it will tend to be full rank. Ah, yes. Thank you, Finale. I need to slightly modify this expression because I wasn't clear about what this action is. That's a bug. So I'm going to delete something up here and rewrite the rest of this expression. It's very important that this is the action that's prescribed by the policy, not just any action. Okay. So if you're taking notes, make sure you write pi s here, not just a. It's the action prescribed by the policy. Okay, so that's the policy evaluation step. You can use Gaussian elimination, for example, which runs in number of states cubed to solve. But now, okay, let's talk a little bit more about the trade-off between policy iteration and value iteration. Policy iteration tends to require fewer iterations than value iteration to solve for optimal policy. Let's write down the following equations to compare this. So reminder, the value iteration is doing the following thing. And let's also talk about the computational complexity of this. This update is going to take of order the number of states, because you do this for every state, multiplied by the number of actions, because for every state you have to maximize over the number of actions, multiplied by, you have to calculate the summation here. You only have to sum over the number of reachable states S prime, for which there's a non-zero probability of transition, so multiplied by L per iteration, where L, as I said last lecture, is the maximum number of reachable next states. So that's value iteration. Policy iteration does the following. Notice it looks almost the same, except we're iterating the policy rather than the value. But there's a huge difference. The huge difference is what goes there. When we do policy iteration, we've already done this expensive evaluation step. We've figured out kind of the global properties over the whole problem of the current policy pie. Value iteration is not doing that. It's propagating information kind of in a more lazy way as the iteration works. What is the computational complexity of policy iteration? Well, I've got the same piece because I've got the same update, but then I've also got number of states cubed because I need to do something like Gaussian elimination to solve the system of equations to do the policy evaluation step. So this piece here is policy evaluation. So that's the trade-off on the question that I got a few minutes ago from Andy. Policy iteration will give you the optimal answer in fewer iterations. It will be more computationally expensive per iteration. You know, the right thing to do, the right place in that trade-off space will depend on the particular MDP, but often will tip in favor of policy iteration over value iteration. But it will depend on the particulars of the MDP. That's what I wanted to say about planning. Do any of you have any questions before we start our discussion of reinforcement learning?
Can you scroll up a little bit to look at the vector form again?
Which gives me an excuse to write my little vector underlines. Does that make
Great,
sense?
thank
Al?
you.
Yep.
Yeah.
Okay. Great. All right. Let's talk about reinforcement learning. This is one of the hottest topics in AI these days, and is increasingly getting attention in applications. RL always used to be viewed, let's say 10 years ago plus, as this kind of really cute, beautiful idea, but nobody thought it was applicable. And then since we've now been able to use things like neural networks to generalize across state spaces in a way that I'll talk about a little bit next lecture, RL has suddenly become much more applicable. So what is the idea? The idea is that you learn from the environment with no knowledge of R or P, the model. Right, earlier it was a little bit loose. I want to use model, not to refer to the states and the actions, just to the reward function and the transition function. That's what I mean by model. So I don't give you access to the model when you're doing reinforcement learning. This leads to a new challenge, which is you have to balance explore, which is learning new things. Try to think about when you were a freshman, when you were a first year on campus, exploring, trying to learn new things to do, new places to visit, and you're exploiting. Now, that sounds like a bad word. I don't mean it in a bad way. You're trying to leverage what you know to do well. So you often hear people talking about this explore, exploit trade-off. And that's something that comes up in reinforcement learning that didn't come up in planning, because in planning, I gave you everything you needed to know. You had no learning problem. Now you have a learning problem. All right. So there are two main approaches to this. One approach is model-based, and one approach is model-free. You might be thinking, well, wait, he just said that you don't have a model. Well, you could try to learn the model, and that's what model-based means. So when you're doing model-based, you try to learn the model. So you want to be able to predict the next state, the next action. Sorry, the next state and the reward. And you use planning. You roll out your favorite planning methods. You deliberate using your model and you decide how to act. So you use planning to decide how to act. That's model-based. Model-free, you don't learn a model. What you do instead is you directly learn a policy or something that lets you understand the right policy, which is, I'm just going to call for now, an action value function. This is going to become what we'll call the Q function. I almost dare not go here, but I can't resist it. Not to be confused with QAnon. Okay, probably shouldn't have gone there, but you're going to see a lot of Q functions coming up with a capital Q, not QAnon. All right, what's good and bad about these techniques? Good, model-based can accommodate changes easily in rewards transitions. Somehow, if you learn that the rewards changed a little bit or the transitions have changed a little bit, you just kind of absorb that into your model and you replan and you know what to do in the world again. But the problem is that model-based approaches are costly and have lots of computation because you're doing all of this explicit deliberation. Because you're planning. Model-free approaches, on the other hand, are simple with inexpensive computation. But the downside of them is that if something changes, you kind of have to, I'm just going to say it roughly as act a lot to learn a new behavior. You have to somehow learn by doing. Suppose that something changes about the layout of the Tercentenary Theater. You know, you can no longer walk through the middle of it. And so when you're running late for class, if you're doing model-based, you just kind of update your model of that and you replan and you know you shouldn't go that way anymore. But if you're doing model free, you have to kind of trace new paths and kind of understand by doing and by updating your beliefs about the right policy, how to respond. And today we're going to be talking about model-free methods. Model-free methods tend to be those that are getting most attention, but I also want to say that I'm painting this at the moment as a stark choice. Do this way or do this way. You can actually combine the two. I'll talk a little bit about that next class. So let's talk now about model-free reinforcement learning. And I'm going to talk about value, what we'll call value-based methods. And what I want to do in the last 10 minutes before we go to concept checks is I want to introduce for you two core central algorithmic approaches for reinforcement learning. One is called saucer and one is called Q-learning. So the idea is going to be that we're going to learn a Q function. Now, what is a Q function? Define two types of Q functions. One is the Q function QPi for a policy pi. Very like things you've seen before. It's the value of taking A followed by policy pi. So it's similar to what we've done before, except usually what we've done is we've put a max A around all of this and said that or I guess what we would have done here normally is we would have put pi of S here. So we would have been writing V pi down, and we would be insisting that we're following the action prescribed by the policy. Now we're writing this down as the value from taking any action A now, potentially deviating from the policy, but then following the policy. That's what this is. And then I can also write down the Q function corresponding to the optimal policy, Q star, which again is the value of taking any action now, but then continuing according to the optimal policy. So I've got these I've got this idea of a Q function, value of taking an action, and then following according to a policy. And I can define that also for following according to the optimal policy, in which case I write it down with a star. And you can write down the optimal policy given this. And the value of the action that maximizes the Q star function. Okay, so the point of all of this is that if I give you Q star, then again, you can read off the optimal action. And there's a Bellman equation that we can write down for Q stars that looks almost identical to the one you saw for V stars. Okay, so this is my Bellman equation. This is my principle of optimality or my consistency property for Q star. It says that the Q star, the value of taking action A now, followed by doing the optimal thing in the future, should be the value for taking action A now, plus the discounted expected optimal continuation value when I optimize the action in the state that I land into. So notice that this is equivalent to V star S prime. So that's our Bellman equation for Q star. And you'll remember that when I had my Bellman equation for V star, then through value iteration, I just kept iterating to try to find a fixed point. I was able to plan. And we're going to kind of think about reinforcement learning as doing something similar to that, but with the Bellman equation on these Q star values. So let me give you just a high level recipe for a reinforcement learner. We will initialize Q values. And think about this just as a tabular representation. Just for every state, for every action, you're going to keep track of a number. And then repeat one act based on your Q values. 2, use the feedback you're getting from the environment, state, action, reward, potentially next state, next action, to update Q values. The idea will be you're hoping to better approximate Q star. Because if you can somehow learn Q star, then you've learned how to behave in the world. And Justine's asking, wait, she thought we didn't know the reward. Well, I don't give you the reward function up front. I don't give you the transition function up front. But as you act in the world, like, oh, that was good, I got a reward. Oh, that wasn't good, I got a negative reward. So you get rewards as you act. So that's your data. Your data begins to accumulate as you behave in the world. If you want, you can think about your robot in your room and you're providing the reward feedback to the robot. Okay, that was good, that wasn't good. So I just want to describe 2 things to you. One is how we might act, and how we might act is via an epsilon greedy agent. With probability 1 minus epsilon, it takes the myopic optimal action, and otherwise it takes a random action. Think about epsilon as being 0.1. So sometimes it will randomize. And it will do this because it knows that it needs to explore. It shouldn't just be exploiting. So that's how we'll think about acting. And then 2, I need to learn Q star. And we're going to do this through this kind of important idea of temporal difference updates. This is where I want to describe now for you 2 approaches, and then we'll go to concept check. One approach is saucer, which is an on-policy approach. Each time you get a new experience, and the name is the way to remember this. Here, the new experience will be S, A, R, S prime, A prime. Third state, you took an action, you get a reward, you landed in the next state, you took the next action. That's literally where the name of the method comes from, saucer. And now how do we do our Q updates? It's going to look a little bit like a gradient step. So this is our learning rate. Alpha sub t, where we've been acting for t periods. This here is a 1-step estimate of Q pi SA. So one-step estimate of the Q value for the policy that you are following. You just got a reward, and then what do you estimate to be the Q value of the state that you landed in and the action you took from that state under the policy that you're following. And then we think about this whole thing as being the temporal difference error. So read this whole thing as estimate of Q value for policy pi minus what I currently think the Q value is. And if this value here is larger than this value, then I'm going to increase Q. If this value here is smaller than this value, then I'm going to decrease Q. So that's SARSA. And then the other methods I want to describe is Q learning. Now, the way this works is each time you get new experience, and let me say that we'll call this off policy. I'll explain this language before we wrap. Each time you get a new experience, now it's just state, action, reward. You do the following update. Actually, I need my next state as well. So now this is where things differ. This is a one-step estimate of Q star SA, not Q pi because of this max. That's the crucial difference between the two methods. And again, we'll think about this whole thing as being the TD error, the temporal difference error. And to summarize these two methods, SARSA is on policy because it estimates Q pi for the policy followed. And remember we said that we have this epsilon greedy agent. So this including epsilon exploration. So if you're doing a little bit of random exploration, that's the policy that's giving you the A prime that you're implicitly estimating the Q values for when you do SARSA. And Q learning is off policy because it estimates the optimal Q value, Q star, while following some potentially non-optimal policy pi, and it will converge to Q star as long as states and actions are visited often enough. So the learning in Q learning works away from the policy that you follow. The policy gives you data that kind of represents the transitions in the world and the rewards in the world. But because you have this maximization within your update step, you're trying to learn the optimal policy, the Q values corresponding to the optimal policy. So it learns away from the policy that you follow while you learn. That's why it's called off policy. So I think that was probably slightly rushed, but hopefully not rushed enough that you don't mind spending 3 minutes on a concept check before you run. So let me describe the concept check to you. Here's the concept check. Here's a grid world, and there's a start state, a goal state. The goal state gives value 10. There are these bad states down here that give -100. Think about this as a cliff. You don't want to fall off the cliff. Discounting, let's say, is 0.9. And again, actions have some noise. You don't necessarily move in the direction that you try to move in. And then we're learning with an epsilon greedy agent. Okay. Question 1, for moderate actuator noise, say noise 0.5, is the optimal policy to go from the start state to the goal this way or to go this way? Question 2, for small actuator noise, actually zero actuator noise, optimal policy this way or this way? These are about planning. These are not about learning. Question 3, what policy will epsilon greedy saucer learn with an actuator with no noise? Say you're using epsilon 0.2 when you follow saucer. Question 4, what policy will epsilon greedy Q learning learn, again, for an actuator with no noise, and say with epsilon 0.2? So that's the concept check. Let me share the link with you all. Okay, link is there, and set up the breakout rooms. Okay. Okay. So you all got this correct. You would go on the top path here. If you have a noisy actuator, if you're a planner, you all got this correct. You would go on the right path here. If you have a non-noisy actuator and you're a planner. And then most of you said that the right answer to question 3 was to go straight to the right, and that the right answer to question 4 was to go straight to the right. And in fact, you have the answer correct for question 4, but for question 3, and it's somewhat subtle, and I went through it quickly, so don't feel bad if you didn't get it. Question 3, actually, epsilon greedy saucer, even with an actuator that has no noise, would go upwards. And the reason is it's because of this on-policy property. So because of the on-policy property, it actually doesn't like the path that tries to go to the right, because when it follows that path, because it's doing epsilon greedy exploration, and that's part of the policy, it will sometimes fall off down the cliff. And so the value function that it would learn in this on-policy sense, given an epsilon greedy policy, would suggest that this is a bad thing to do. Whereas the value function it would learn for this policy, even though it's doing in this on-policy sense, this random exploration, would be much better. And so the right answer to this question is around the top, even with an actuator that has no noise. You can think about it as it's not able to tell the difference between an actuator without noise or an actuator with noise and a policy that's doing random exploring. And then the right answer for question 4 is to the right, because Q-learning is this off-policy learning method. And it doesn't matter what the policy is doing while it acts in the world and collects data. It will still learn the optimal policy through the Q star function. And so as long as it visits enough of these states often enough, it will learn that this is the right thing to do with an actuator that is not noisy. And so that hopefully gives you some intuition for the difference between off-policy and on-policy learning. Sorry we went over. I wanted to get through all this material and I badly mistimed class last week. So I thank you for your patience, and I'm happy to hang around for a few more minutes as well.
Thank you.
Thank you.
Thank you.
Thank you.
Congrats, Steve.